I don't know if you remember. So the 2.1 is already due. It's already due just now. 9 o'clock. 2.1 was due. But I struggled with the last one. Remember number 20? You could get the answer right by just guessing around. But I wanted to show why the book is actually right here. Math Excel is right, and I was thinking wrongly. Is that a word, wrongly? I was not correct on this one. Here's why. Here's what fooled me. Notice it says graph 1 period of the function. Okay. Now for cosine or for sine, what is 1 period? Or what's the formula for, it's period equals 2 pi over t, right? That's always, well, we say b. There's other versions of the formula. We say 2 pi over b, don't we? Y'all with me? Right, that's the formula. We do the ABC thing. So in other words, the A is 9. Can you see the here, let me make it a little bigger on there. So here, let me rewrite it up here. So this is y equals absolute value. The trick is this one has absolute value. And I'm going to write the x over 2 as a half x. That way it's just easier to see that A is 9, B is a half, in the ABC thing. So A is 9, B is a half. That a half x is the same thing as x over 2, isn't it? So, all right, so B is a half. So the formula then for period is 2 pi over B. Now the trick is, that's for normal cosine. You'll see as we go. That's what fooled me. So the period is 2 pi over B, and which is going to be 2 pi over B. B is a half. You know what you do the half? You flip the half up. 2 pi times 2 over 1, which is just 2, which is 4 pi. Right? So the period is 4 pi. Excuse me. Excuse me again. Well, for normal cosine of a half x, if there wasn't the absolute values, that'd be true. Let's graph it. So now we'll see as we graph. So as we go to graph the thing, so I'm going to go from 0 to 4 pi because, that's the period. Right? That's what we normally do. We normally do one, and that's what they're asking. Do one period of the function. So I'm thinking, okay, that's what fooled me last time. I'm just going to go 0 to 4 pi. I just found the period's 4 pi. Just go 0 to 4 pi. Here we go. What does cosine always do? The only difference between sine and cosine is how they start, Sine starts at 0, but this isn't sine. Cosine starts at the top. So he starts up here. He goes down and up during his cycle like that, right? That's what cosine always does. And he'll go at 9, so this will be up to 9, down to negative 9. Now, it's really absolute value, so it's going to flip that bottom part up. I'll get to that in a minute. But so far, so good. That's just, if they just asked me 9 cosine of a half x without the absolute value, if there was no absolute value, that'd be it. We'd be done. That's correct. But now I got to think about what absolute value is going to do. We good to there? Does that make sense? Right? I found the period is 4 pi. 2 pi over b came out 4 pi. So I go from 0 to 4 pi. Cosine always starts high, ends high. If this was sine, I would start at 0 and end at 0 and hit 0 in the middle as well, for sine. But cosine starts high, ends high. So there would be 9 cosine of a half x goes up to 9, down to negative 9. But now we think, oh yeah, but it's really absolute value. So we know what absolute value does to anything. It makes this negative part go up instead of down, Makes the negative numbers positive. Makes everything positive. And that's correct. That's true. So let me alter it that way. And that's what I did for you last time, in class. And then I stopped and I went, well, C's not right then. C's not right. They didn't go far enough, right? They only, if you look at it, here's what fooled me. They only did this part of it. Well, my graph doesn't look so good. Let me draw it a little better so you can you kind of see what I'm talking about? I got to be a better artist here to make that clear. So what they did is, let me see, this would be halfway, quarter way. Let me make it a little more. Yeah. Like that. So they only showed, that's a little better. They only showed this part of it, didn't they? That's the answer they have right there. Why'd they only do half of it? The period's 4 pi, and they said up here, graph 1 period. That's why I was having a problem with C. I don't know if you noticed any of this. Maybe you're thinking, I didn't notice any. I don't know what you're talking about, Mr. Aaron. But hopefully some of you are. I don't want to waste time on just talking to myself up here. But anyway, the deal is you see that the period changes when you do the absolute value. That's what tricked me, right? Notice it repeats itself now every 2 pi, right? Let me just circle. Aren't those two identical? It suddenly changes the period. That's what I didn't notice. When you throw the absolute values in there and it flips everything up, it actually means it repeats itself now every 2 pi, doesn't it? Because this is a repetition of that. So that's why all they did was graph this part, and that indeed is one period. They're right. That's what was throwing me off. All right. I'm getting the feeling you're like, oh, I don't know, whatever, Mr. Aaron. All right. So come see me if you want to talk more about that. That's over. We better move on with, since you haven't had any homework on this yet. Okay. So there we are, back with tangent. So remember, we've been learning about what tangent and cotangent do. Well, tangent so far. And what tangent does is, remember, it has the two asymptote lines. That's going to be super important, between negative pi over 2 and positive pi over 2. And it does the snake thing in between. So there's tangent x, right? That's the basic one, without any shifts or movements or anything like that. So you want it, that's what you want to put in your 3x5 card, is the basic tangent graph. And same thing with cotangent and secant and cosecant, which we're going to do all those today, is the plan in these 2 hours together, or an hour and 50 minutes. So there's the basic tan. And let me just tell you right now, and then I'll get more detailed with it in a little bit. Bless you. Tangent is going to, notice how it goes from negative pi over 2 to positive pi over 2, and that's the focus zone. And then after that, it just repeats, right? Over here, there's another snake and another snake off to the right. It just keeps repeating that snake, 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 snake thing like that. So we're just graphing. All we do with these trig functions is graph one period, one cycle, and the rest repeats to the left and the right forever. So tangent, getting back to my main point, tangent, notice, goes from negative pi over 2 to positive pi over 2. That's exactly the zone of importance and focus we're going to find for secant in a few minutes. Tangent and secant will both go negative pi over 2 to positive pi over 2. And then, in just a second, when I do cotan, he's coming next, cotan will, all the graphs today, all the graphs in this section, we're doing the other 4. Right? Yesterday, or a couple days ago, we did sine and cosine. There's 6 total trig functions. We've only done sine and cosine in detail. Sine and cosine. This section, we're doing the other 4. Tan, cotan, secant, cosecant. So I'm giving you the big picture now. The other 4 all have vertical asymptote lines. They're all going to have this same kind of thing where you have these 2 dotted vertical lines. And what do those mean? Those are lines the graphs may not cross, will not touch. That's what vertical asymptote lines do, right? So it's going to become of great importance to find out where are those vertical asymptote lines for the various graphs. You want to put them all on your 3x5 card, of course, but it helps just to know it cold as well, I think. Tangent, negative pi over 2 to positive pi over 2. Secant's going to be exactly the same thing. It won't do a snake. It'll do something else in that zone. But it'll be negative pi over 2 to positive pi over 2 for what secant does as well. Cotan is also going to have 2 verticals. From 0 to pi is where he's going to do his thing, which we'll get to in a minute. And the other one, the other who's the other one? Cosecant. That's how I'm memorizing it anyway. You don't have to, again, you get your 3x5 card. But it also goes from 0 to pi. So I'm just remembering both the co-functions, among the other 4. We've already done sine and cosine. We know about them. But among the other 4, the 2 co-functions both do vertical asymptote lines between 0 and pi. Both the non-co, tangent, that doesn't have a co in front, and secant, that doesn't have a co in front, both the non-co do their vertical asymptote lines between negative pi over 2 and positive pi over 2. Does that make sense? So that's and I'll show you all the details as we go, but just kind of setting that in stone right now. You're knowing what to expect. All 4 of these are going to have the vertical asymptote lines, secant and tangent between negative pi over 2 and positive pi over 2. The 2 co-functions, both between 0 and pi. I like patterns like that. I like organization. It helps me keep things straight. So maybe that helps you as well. All right, let's get back to this particular question we have in front of us. Tangent. So we got the basic look of tangent here between negative pi over 2 and positive pi over 2. So that's the basic look of tangent. What does it do to do the x plus pi over 5? Well, remember how we handle? We're going to handle all four of them the same way today. We did a little bit last time. That is, we take that piece. I'm kind of running out of room. I'll just try to squeeze it in right here. You do the x plus whatever they have in the parentheses here, whatever they have, you say, okay, that's going to be between negative pi over 2 and positive pi over 2. Right? Remember we did this last time? That's what we're going to do all four today. We're going to find where are those verticals, what's inside the parentheses, stick them in the middle between where the two verticals are. So if this question was a tangent of, of something or a secant of something, either way, I'm going to take the same first step. I'm going to stick whatever's in the parentheses between negative pi over 2 and positive pi over 2. I'm hearing a little noise up here. Please make sure the people around you are not distracted. Okay, so is that making sense there? Is that good? So now if this was if this was the two cofunctions, which we'll do in a few minutes, cotan and cosecant, make sure your whatever's in the parentheses goes between 0 and pi, and then solve. Is that making sense? That's always our first step. Notice what our first step is not. It's not what we did for sine and cosine. Where we did like the period, 2 pi over b, and the phase shift, negative c over b, and all that. That's what we do for sine and cosine. That's the easy way to get your hands on the graph for sine and cosine. It's a different method for these other four trig functions. That's a lot of the battle in math classes, is identification and process, right? So you guys get in the game plan. So when you take the next test, whenever that is, a couple weeks, right? What's our next test is? Yeah, 2 weeks. Yeah, 2 weeks from today. Yeah, 2 weeks from today, when you take the next test. So chapter 2, and you have all these graphs everywhere. So you're going to want to think, okay, if I get a sine or a cosine graph question, my first step is the period 2 pi over b, phase shift, negative c over b, all that stuff we did for sine and cosine. If I get the other four, it's all about sticking what's in the parentheses between either negative pi over 2 and positive pi over 2 for tangent and secant, or 0 and pi for the two cofunctions, cotan and cosecant. Making sense? And then you solve. Okay, so now how do I solve this? It's called a compound inequality, right? Compound just means big. Like if you break your leg bad, they call that a compound fracture. So this is a bad inequality. It's a compound inequality. Three-parter, right? How do you solve it? What are we going to do? Got to get x alone. So that's what x is always saying, huh? I won't be alone. Get rid of the stuff. So subtract pi over 5. Huh? Subtract pi over 5. Subtract pi over 5. From all three, gonzo in the middle. And so what does that leave on the two sides? How do we do pi over 2 minus pi over 5? You got, a lot of your guys' calculators will do this for you automatically if you don't want to mess with fractions. You could just go a half. You could just throw the pi in later. Just say, look, this is a half over a fifth. I'm sorry, not over. This is a half minus a fifth, Hit the buttons, the fraction things on your calculators. When you're all done, throw the pi back in. It'll tell you, what, 3/10? Then you throw the pi back in. Anyway, I'll do it longhand. I think we did it yesterday, Monday. So you multiply top and bottom of this one by 5 and top and bottom of this one by 2, right? You got to make both denominators 10, right? So this will be 5/10 pi, which is the same as a half, minus 2/10 pi, which is 3/10 pi, isn't it? Can you read all that? The other side, same thing, top and bottom by 5, top and bottom by 2. So that's what? Minus 5 pi over 10, which is minus a half, minus 2 pi over 10. And so that the left ends up minus 7 pi over 10. The right here, ends up 3/10 pi. So what does that mean? Well, that's where the two vertical asymptote lines end up being for the snake tangent graph. They're shifted because it's not just tangent of regular x. Tangent of regular x goes from negative pi over 2 to pi over 2. But when you throw that x plus pi over 5 in the parentheses, it shifts where the two asymptote lines are. So now we can draw the graph. So now we go, all right, we got it. Well, in fact, we can just grab it, huh? It's whichever one goes between negative 7 pi over 10 and 3 pi over 10. Which one is that? Can you tell by the picture? It looks like A, isn't it A? Yeah, it's A, right? You know what I mean? So it's negative 7 pi over 10 and positive 3 pi over 10. Right in the middle of that, which is about right here, it's not the origin, is it? It does its snake thing between those two bounds. That's where the vertical, sorry, I'm being a little scribbly there. That's where the vertical asymptotes, the two dotted lines, are. Yeah, I'm still being scribbly. 3 pi over 10. There we go. And this one's negative 7 pi over 10. That's where they are. Isn't that A? See how A has minus 7 pi over 10 and 3 pi over 10 is the two verticals? And there we go. Just going to be multiple choice in this section. I think, we'll see as we go. I think they're all multiple choice. That's how the test will be for sure. Questions on that one? Is that good? Do you guys know what I mean by the calculator thing? Maybe it's worth it to take just a second. Have I done this? I did? I should undo the fraction makers? Yeah. Oh, I did. With the, okay, well then, good, we won't waste some more time. Yeah, so you know what I mean by that? So you can just go a half minus a fifth on your calculators with the fraction maker buttons, right? Most calculators have them. If you're not sure, grab me after you. If you missed me saying that before, then and then just throw the pi in afterwards. Save some, make it quick and easy. Questions on that? We good? First, just mention what's the difference. So we have tan again, tangent of x, y equals tangent x. Let me just write it again real quick. Vertical lines, minus pi over 2 to positive pi over 2, and it does the snake in between. All right. Cotan, now we're on to cotan. We're doing all four today, the other four. Cotan, as I've already told you, his two verticals, all the graphs today have two vertical asymptote lines. His two verticals go from 0 to pi, as we've already said. Both the cofunctions today have the vertical asymptotes between 0 and pi, cosecant and cotangent. And both the non-cos, tangent and secant, are negative pi over 2 to positive pi over 2 for their two vertical dotted asymptote lines. Okay. And then what does cotangent do in the middle of that? He does a snake again, but it's an upside down snake. He goes like that. So he does the snake upside down. There it is. So I'm not taking time to prove all that to you. You know, you could take an XY table and plug in the cotan, and I'd be glad to do that with you office hours. If you want to see all that, I'd be glad to talk about all that with you to show you why he does the upside down snake. You might wonder, like, why is he doing? That's just what he does. I mean, if you make an XY table, you know, and you plug in angles, you know, between 0 and pi radians, so I could do degrees, 0 degrees, 30 degrees, 60 degrees, 90 degrees, right? Pi's 180, keep going, 120, 150, all the ones we know are 180, that's pi, right? If you plug those in and you get your y values, you'll find out that, you'll find out that you get a bunch of dots like this. This is what you will find when you do that. So he does an upside down snake, cotangent does. So tangent is regular snake, cotan is upside down snake. All the cofunctions go from 0 to pi. So there's the game plan. So that's what you want to put, that's what I would probably put on my 3x5 card, you know. The basic tangent, the basic cotan, and then you can handle the shifts and stuff by just sticking whatever's in the parentheses between 0 and pi and solve them. Make sense? That's how the basic look, and you handle it from there. All right, so I'm going to move the screen if that's okay. So let's try the question before us, question number 4. They want us to mix and match those 4 cotangent ones. Okay. Notice, a couple things to notice. What should we notice? First off, this one and this one have negatives in the front. The other two don't. Notice that first off. That's a big deal, huh? Negatives in the front of the cotangents. What does that mean? That's a flip. So normal cotan from 0 to pi again, 0 to pi, is the upside down snake. That's normal cotan. So then down here, or over here, I'll show negative cotan then. Negative cotan is going to kind of look like tangent, right? It's going to flip it back. Like that, isn't it? That's negative cotan. So first off, the two negative cotans are going to be the normal looking snakes. Normal meaning from left to right, they climb instead of fall. right? The normal way we do it is if you're a little person walking on the hill here, from left to right, you're climbing all the way. That's normal tangent. Normal cotan, from left to right, you're falling all the way. It's a slide, I guess. All right. So anyway, so first off, which one is negative cotan? Can you tell? It's got to go from 0 to pi. And there's been no shifts of any kind. There's nothing in the parentheses here. So it's not moving the vertical asymptote lines at all. They're just stuck between 0 and pi. 13? Yeah, it looks like 30. It's hard to, I don't know if you guys can see all that. I can make it bigger. That'd be helpful. Huh. All right, there we go. Yeah, can you see now? Yeah, it looks like 13, huh? 13, because 13 goes from, yeah, it doesn't say pi, but this is pi over 2 in the middle, so this must be pi here. This must be 0. He's doing the normal snake, which is negative cotan. So, yeah, this one must go here. Good, let's try, how about this other? So then there's only one other one that is upside down. It must be that one, huh? Because that's the one. I don't even have to fool around with the shift or anything. That's got to be him. Because these other two are going from high to low like cotan normally does. Right, high to low. Okay, so then which is which? Well, I got to look at the bounds. Let me just do that. I'd rather not mess with the fractions. Let me do this one first. He doesn't have any fractions. He looks easier. So I'll just do him first. So what do you do? You take what's in the parentheses. Remember, for all 4 functions today, you put what's in the parentheses and you put it between wherever the vertical asymptotes normally are. Where are they normally for cotan? 0 and pi. Is that making sense? That's what we're going to do this whole section. Secant, cosecant, tangent, cotangent. You just put what's in the parentheses in the middle of where the 2 vertical asymptotes are, which is 0 to pi for the 2 cos, cosecant, cotangent, and negative pi over 2 to positive pi over 2 for the 2 non-cos, secant and tangent. Okay, then you solve. So minus pi, minus pi, minus pi. 3-parter here. Gonzo, x, negative pi to 0. So basically this one goes, what am I doing here? This one goes from negative pi to 0. Which one goes from negative pi to 0? I don't know. Yeah, it's hard to see, but it's this one. Does everybody see that? Now, it's a little bit off the screen. Let me help. Let me explain what that means. So it goes from negative pi to 0. So upside down, cotan's upside down. So it's like that from negative pi to 0. But then it keeps repeating. Remember, these things repeat forever. So next will come another upside down snake, which must go 0 to pi, and on and on it goes in both directions, huh? So that is this one. You see, here's the first one right here. You can barely see it on the screen, right? That must be. How do I know that's negative pi to 0? Well, because halfway through is negative pi over 2, isn't it? Everybody see that? Okay, so we got it. So this one must be 15. Good? Okay with matching those up? I'm making sense? All right, so it's all, I'll move on if that's okay. No questions? Good? Okay. All right, this is question number 5. So y equals 1/5 cotan 3x. So what do we do first? What do we do? Yeah, let's don't worry so much about, with the graphs that we're dealing with, we don't worry so much. Yeah, I'm glad, it's a good question to bring up. Sines and cosines, what we did, was that last week? Last week, sines and cosines, we were really into the amplitude on the front. Because why? Because the sines and cosines did not go up forever. The graphs we're dealing with today, all 4 of them, will go up forever and down forever. Therefore, the amplitude, although it still makes it go up faster, or up a fifth will make it go up slower, right? It'll compress it. But still, it's going to go forever, though. So it doesn't make a big visual effect. Amplitude doesn't, isn't really going to be very helpful to us on, distinguishing among the multiple choice options, because they're all going to go up forever eventually. Just won't do it quite as fast. So don't worry so much about amplitude for these graphs. The focus is mainly right there. So what do I do with that to know which one's right? So what do I do with that 3x? Between 0 and pi. And you solve, right? Because cotan is between. So give that a try. Solve for that. See if you can figure out which graph is right. So again, all these graphs go up and down forever. All 4 today go up and down forever. So amplitude isn't that helpful. So solve for x there. And then pick the right option. Give you a second. Feel free to check with those around you. We're doing okay? Just divide through by 3. And 0 over 3 is 0. These cancel. Pi over 3. So basically, it's going to, come down here and draw it. It's going to go from 0 to pi over 3. The 2 verticals, right? We're always finding where the 2 verticals are for the 4 graphs today, right? That's going to go from 0 to pi over 3. It's going to do, remember, cotan does upside down snake, unless he's been flipped or something. This one has not. The 1/5 will just mean it doesn't go up and down quite as fast, but it's still going to eventually go up forever and down forever. And it's just going to keep repeating that. 0 to pi over 3. It's just this one right here, isn't it? Wait a minute. What's this one looks the same. What am I missing? Oh, no, that one's off a little bit, isn't it? That's weird the way they do that option. Don't you think? I mean, it's still 0 to pi over 3. They just didn't, they made it not hit the middle. Well, that's wrong. It hits the middle. That's kind of a dumb thing to do, I think. Anyway, so there it's this one. It's B. It is B. It always hits the middle of its 2 asymptotes. So never grab the one that's not hitting the middle of its 2 asymptotes. That's always wrong. All these graphs do their thing in the middle of the vertical asymptotes. They never do that. I don't know why they keep doing that. That's never right. No situation will that ever be right. All right, so it's B. Good? Easy enough? All right, try that one. 4 cotan x plus pi over 3. So don't worry about 4. You know what to do. Just grab the x plus pi over 3. Plop it down in the middle between 0 and pi. All right, we doing good? X plus pi over 3, that's in the middle between 0 and pi. So we solve for x. We get the 3-parter here. Subtract pi over 3, subtract pi over 3, subtract pi over 3. That leaves x. This is minus pi over 3. The other side, how do we do pi minus pi over 3? Couple of ways. I'll do it formally. You can do it with your calculator, or you can just kind of think about it informally. Let's literally think about pi. This is a whole pi. Take away 1/3 of a pi. If I said I got a whole pi, and one of my kiddos snuck in and ate 1/3 of the pie, how much is left? 2/3 of the pie, right? That's all I have left to eat. 2/3 of the pie. So, right? I mean, you can just say that's a whole pie. Take away 1/3 of a pie. 2/3 of the pie is left. 2/3 of a pie. Done. Get right. That's true. If you can think well that way, great. Just do that. If you're not quite sure about that, then let me put it back the way it was. It was pi minus pi over 3. So the more formally how you would do it, anytime you have like a whole number or a whole pi interacting with a fraction, you put this over 1 to make it look like a fraction. You good with that? And then multiply top and bottom by 3. So then it becomes 3 pi minus 1 pi over 3, which indeed is 2/3 pi. Good on that? Or on your calculator, it's just 1 whole pi minus a third, just 1 minus a third, which is 2/3 of a pi. All right, so any which way you want to get it, it ends up going from negative pi over 3 to 2/3 of a pi. So draw that graph. So negative pi over 3, and then a little bit further to the right of that, 2/3 of a pi. And it's going to do cotan, does the upside down, right in the middle of that. It's going to do the upside down snake. So which one is doing that? Is it B? No? It's hard to tell. They kind of, C looks like it. B and C, here, it's not A and D. They got the snakes going the wrong way, right? It's either B or C. They both are upside down snakes. Now I mean, you'd have to blow them up. They're all kind of messed up. But it sort of looks right. B and C, don't they? What's the difference?
It's the amplitude. C goes up faster.
Oh, so we do have to worry about the amplitude a little bit. Okay. Yeah. Yeah. So it is C. Oh, that's tricky. They're being a little more tricky. Okay, yeah. So we do have to worry a little bit about the 4. So remember what a multiplier does in the front of something, right? If it was sine or cosine, it makes the top and the bottom bigger, but these go up forever. So that for these 4 functions, it just goes up and down faster when you have a multiplier that's a number bigger than 1. If you had a 4th there, it would go slower because it's only going to go up a 4th of the speed. But this one's a 4, so it's going to go up 4 times as fast. So the answer is going to be C. You'd have to blow them up. Let me go back if that's our question as we look. So one more time, as we look at B and C are identical in most respects. They have the right vertical asymptote lines, negative pi over 3 to positive 2 pi over 3. The snakes are going the right direction in both of them. The only difference between B and C is B hugs the x-axis longer, is slower to go up. C goes up faster. Since we have a 4 in the front, that's going to make it go 4 times as fast up. We grab C. Good on all these? Okay. Yeah, so what they're doing on this, well, you know what, let me just describe it with a blank screen. I think it would be best. So we're going on to secant now. So we did tangent, cotan, now we're going to do secant and cosecant. How do you know what the graph of secant even looks like? There's actually a nice little trick which everybody uses, and it's really nice. For secant, remember secant is 1 over cosine, or cosine is 1 over secant. Either way, same thing. Right? They're the upside downs of each other. So therefore, whatever the graph of cosine, if you flip it, you get the graph of secant. So I'm just going to show you how they came up with it. How'd they come up with it? Well, start with the graph of cosine. What's the graph of cosine? You know cosine. He starts at, no, he doesn't start at 0. That's sine. He starts up here at 1, and then he ends at 1. And halfway he goes to the bottom halfway, and then over here he'll be back up. So he goes, I can do this at a quarter mark and a quarter mark. So he goes down like this and back up like that. So there's cosine between 0 and 2 pi, right? That's cosine. Y'all with me? That's just, here, the black one. I'm going to do another color for this. So that's cosine of x between 0 and 2. Does the U shape between 0 and 2 pi, right? Now, secant, I'm going to change the color. So secant of x, what is secant? Well, he's upside down of cosine. Now remember, this goes up to 1 and down to negative 1, right? So what does that mean? That means upside down the y values, because this is y equals secant, and y equals 1 over, oops, kind of scribbling there, 1 over cosine x, right? So the y values are flipped. So if you take the y values, if you take the number 1 and you flip it, what does it become? It's still 1, right? Because 1 over 1, flip it, it's 1 over 1, it's still 1. If you flip 1, doesn't change. So my point is, right here at 1, I'm going to start laying the secant graph right on top of the cosine graph now. It's going to be the same, because the upside down of 1 is 1. Okay, but what about right here, where the height is about a half? Wouldn't you agree that dot is up about a half on the cosine graph? When you take that half height, right, and you flip it, what's a half become when you flip a half? 2 over 1. 2. So that's going to be up here at 2. Secant graph's going to be up here. So as these dots got lower, secant's going to get higher. Do you see that? That's what secant graph is going to do. Secant graph is going to touch right here, because 1 over 1 is 1. They're going to meet there at 1. They're going to be the same thing at 1. And as these become fractions, smaller, like smaller and smaller, like what's this one? Let me get really close to 0 here, way down here. What is this dot here? It's 1 over 100, let's say. You know, really close to 0. It's barely above 0. It's just 1/100th. Like if you had 1/100th of the pie. That's like just a crumb, right? So just a little bit. All right. If you flip 1 over 100, what do you get? 100. So where's secant going to go? He's making sound effects, but I'm drawing nothing. Had the eraser on. Boom, he's taking off. Do you see that? Secant is rocketing up. And when you hit 0, when you land the plane at 0, cosine anyway, is at a height of 0 right here. What if you flip 0? What's that do? That's not allowed. Guess what you're going to get there? The vertical asymptote. For secant. Right? Where cosine is 0, secant's undefined. Because secant's 1 over. 1 over 0, right? You can't have 0 in the bottom fraction. That's where our vertical is. Right? Which is where? Pi over 2. Because this is pi halfway. This is 2 pi here. Remember I promised you secant and tangent, the non-cos, are going to be at pi over 2, and it's also over here. If we did the other part, it's at negative pi over 2. So that's what secant's going to do. Same thing over here, secant right here. This is -1. Flip -1, it's -1. You know, I won't bore you with any more details. 0, it's going to do another vertical right here. There's what secant's going to do. Do you see that? See, the secant is the red. It's U-shapes, up and down. Secant is going to do U-shapes up and down. Does that make sense? You see how that's got to be? I'm just getting that by flipping the y values. Right? Again, on the cosine graph, as these dots get lower and lower, like way down to almost 0, like I had almost no pi. I had 1/100th of the pi, just a crumb. Then flip that, 100th. Secant is rocketing up to 100. If you get really close, 1,000th. Well, secant's up to 1,000 now, right? As cosine gets super close to 0, flip that, secant gets super giant. Until right at 0, secant's undefined. So secant rockets up, doesn't he? But they touch at the 1, because 1 over 1 is 1. Same thing at the -1. 1 over -1 is still -1. That's why they touch there. But when secant gets close to 0, when cosine hits 0, that's where the vertical asymptote lines are for secant, because 1 over 0 is undefined. So everybody see that? So the secant graph is a bunch of U-shapes. And where do they sit? Between negative pi over 2 and positive pi over 2. Is the U going up? And this one is at 3 pi over 2 for the U-shape going down. That's the secant graph. We get it by flipping the cosine graph. I mean, you know, flip the cosine graph. You flip the numbers in the y values in the cosine graph. Okay, so with that in mind, let me give you the basic secant plan. So that was the derivation. That's where it came from. Here's what you need to know. Here's what you need to put on your 3x5 card. Somebody gives you a secant graph. How are you going to do it? You remember the secant and the tangent, the non-cos, go between negative pi over 2 and positive. That's what I'm showing you to memorize. Notice Mr. Roberto is here in the back. I just want to point him out. He's there to help you. He checks in. So he checks in every now and then with us. So he's watching the same way. He knows all this stuff on his own already. But he's also just dialing in so he won't show you a different way. If you go see him, he'll help you the same way. So go get help back there. He's got new. Did I mention there's hours changed back there? Did I already mention that? They're a little different hours. They're back there. All right, anyway, getting back to it. So I mentioned the way I'm encouraging you to memorize, you can put it on your 3x5 card, of course, but it's just nice to know it cold on your 3x5 card. For these 4, we already did sine and cosine last week. For the other 4, secant, cosecant, tangent, cotangent, just remember the 2 non-cos, which is secant and tangent. They don't have a co in front. The 2 non-cos, their vertical, all 4 of these have vertical asymptote lines. Their verticals are between negative pi over 2 and positive pi over 2. For the 2 cos, cotangent and cosecant, their verticals will be between 0 and pi, won't they? So put down those dotted vertical asymptote lines. 0 and pi for the two cofunctions, negative pi over 2 and positive pi over 2 for the two non-cos. And what does the secant do in that region? What does he actually do? Well, right in the middle, he does a U-shape up, starting at 1. Remember, because he's the tip of the cosine. And then he repeats the same thing with at negative 1, a U-shape down, and you've got to have another vertical. So that's the trick. He actually has another one going down, and this one is at 3 pi over 2.
It's always at 1?
What's that?
Not always at 1, hold on. Is it always at 1 on the y-axis?
Oh, well, unless they put an amplitude in the front. Yeah, so it's always at 1, but if they throw a number like 2 in the front or something like that, then it would be at 2. Yeah, so if they throw a different amplitude in the front, then that'll change it. Yeah, good question. Otherwise, it'll be at 1. It'll be whatever the amplitude is. Good question. Now I want you to see something here for a second. I'm trying to make this as simple as possible, but I'm sort of oversimplifying. I want you to see where I am. So I'm trying to make it as simple for you to learn it as possible. I'm just harping on negative pi over 2 to pi over 2, and that's true and I think helpful. But remember, secant, you have to show the downward u as well. Technically, this is one full period, not just the up u. You can't just draw the up u and say, I did the one whole period, one whole cycle. No, because he's not just up u, up u, up u, up u, up u. That sounded a little weird. But he's not just that way, right? He's an up and a down, an up and a down, an up and a down. So that's one full cycle. Right now we're looking at one cycle. So you technically have to go from negative pi over 2 all the way to 3 pi over 2 to get a full cycle for secant. But really, it's just a repetition upside down of what happened between negative pi over 2 and positive pi over 2. So if you just know that, I think you'll get it, right? That's what I'm trying to make clear. Is that okay? Whereas tan and cotan, that was the whole story. Boom, done. Secant and cosecant are going to do an up, down. Both of them are going to do the same kind of up, down thing. So there we go. So looking back at, let's do the question now. So this question, they're just giving you cosine. They're saying, hey, flip it. Okay, so I made it secant. There's nothing fancy there. I just flipped cosine to make it secant. And now they're saying, all right, which one of those is really the graph? Well, I don't know. Let me make it a little bigger, and then we'll figure it out. All right, so there it is. Which one of those is really the graph? So what are we supposed to do? Don't worry about the 1/3 so much, but first focus on that, right? All these four, we grab what's inside the function, 3 pi over x, grab what's inside, and put it between what two bounds? For secant, negative pi over 2 and positive pi over 2, right? For the non-co-functions, you grab whatever's being plugged in to secant or tangent, and you make the compound inequality between negative pi over 2 and positive pi over 2, because that's the first two vertical asymptote lines. That's how we do all four of these. We just stick what's inside between negative pi over 2 and positive pi over 2 for secant and tangent, between 0 and pi for the two cos, cotan, cosecant. Solve it. How do we solve this? You guys okay with this one? To go to divide by 3 pi, right? To get x alone, x always stand on one below. Now, what do you do when like it's already, watch me on this. I know a lot of people get messed up. I'm going to show you an easy way to do this. A lot of people go, well, you just divide by 3 pi. That's true. That's okay, but that's not easy. It looks kind of ugly, and it's right. You could make it work. It's true. It's not wrong or anything. But I think you'll find it easier to just stick the 3 and the pi in the denominator. That's the same effect. To divide by something is to stick it in a denominator. There is no difference. And that'll be easier. You just cancel the pi's right away. And look, that's just 1/6. 2 times 3, 1/6. Just easier to do it that way. Same thing over here. Just stick the 3 and the pi down in the denominator. Pi's cancel, and it's negative 1/6 and positive 1/6. That makes sense? Everybody see that? That'll be easier. So when you divide, that means put it in the denominator. Just put the 3 pi in the denominator. So it goes between negative 1/6 and positive 1/6. So for the first two vertical asymptotes. So which two do that? I can't even tell. They're so small.
There's no positive or negative vote for that one?
There's no what?
Since it's positive, like 1/3.
Yeah, so instead of 1 and negative 1, you're totally right. Yeah, so instead of 1, so it's going to go from over here at negative 1/6 to positive 1/6. And you're right, it's going to do a U shape. And instead of being at 1, it's going to be at 1/3. Exactly. Everybody good with that? And then over here, if you keep going, it's going to do a U shape downward. This will be at negative 1/3, a U shape down. And what is this other bound going to be? Well, I don't know if we even need to find it. We could mess around with it. Can you tell, guys? Is it A?
It starts on the y-axis.
Because isn't it like opposite of cosine?
Oh yeah, it is centered on the y-axis, isn't it? Which is A. Good job. Yeah, good observation. I wasn't noticing that. Whereas B is not. See how this U shape right here on B is wrong? It's not centered on the y-axis. See how ours has the y-axis spearing right through the middle of it? That's right. Whereas, which is like what A does. The y-axis spears through the middle of the U. So it's not B because the y-axis does not spear through the middle of the U. It's not D because the y-axis does not spear through the middle of the upward U. It's not C. Yeah, that's it. Good job. That's all we need, huh? It doesn't spear through the middle. Only A.
Blue is like that one for B, and C it's like sine. So secant is cosine. So cosine.
Yeah, right. They're doing sine. I think you're right. They're doing the flip, so it's cosecant. Yeah, you're right. I think they're doing something like that. So our answer is A.
What if you have a phase shift?
Yeah, well then, and you'll find it when you do this kind of thing right here. Yeah, the phase shift, all that stuff will be handled by just sticking whatever's in the parentheses between the two, negative pi over 2 and positive pi over 2 and solving. You'll find where they move. Because a phase shift is a movement.
Yeah,
Of
that's
it.
what I was asking. Would it, instead of starting on the y-axis origin, would it?
Yeah, it will shift it. Yep. And you'll find where the two new bounds are when you solve. But it will move it. You're right on the money. Good. So cosecant. So cosecant is 1 over sine. It's going to be upside down as sine, huh? So just think about what sine does. What does sine do? Starts at 0, goes up, goes down, come back to 0, huh? And this is at 0, this is at 2 pi, this is at pi. That's sine. So the upside down of that, which is what cosecant is, the upside down of sine, every time sine equals 0, cosecant is 1 over 0, not allowed, undefined, vertical asymptote line. Remember that? So everywhere sine hits 0, cosecant is going to be 1 over 0, going to have a vertical asymptote. So sine hits 0 here, so put a vertical. Sine hits 0 here, so put a vertical. Sine hits 0 here, so put a vertical. At 0, pi, and 2 pi. So it's just like I was telling you, right? The two cofunctions, their first verticals are between 0 and pi. Just like cotan, huh? Same thing as cotan. 0 to pi for cosecant and cotan, both the cos. The first two verticals are 0 to pi. For both the non-cos, tangent and secant, it's negative pi over 2 to positive pi over 2. All right. And then what does it do? Same thing. It hits. They touch right there at 1, go up and use because if you flip it, fractions get big. And same thing. So it's the same thing. It's just a shift. Cosecant is just a shift of secant, right? That's what co means, as we talked about, 90-degree shift. The U shapes have just been shifted. So, but you'll remember all that. You'll know all that if you just put on your 3x5 card, 0 to pi. Both the co-functions, the first two verticals, are 0 to pi. All right. So can I move on? So that's what I would put on my 3x5 card. For that one, yeah.
So the red U graphs are the secant, cosecant.
Oh, yes, I'm sorry. You're right. Yes, I should say that. The red is the cosecant. This one. The red is the cosecant. Correct. Red is the cosecant, and the black is the sine. That's right. Yeah, good. Agene, right? Right. Good. Yes. Okay, good. So let's try this one. Okay, so cosecant. So there we go. Again, don't worry so much about the amplitude. It's not really a big, huge deal. What's a bigger, huge deal is whatever's in the parentheses. Take that, x over 3, and what do I put it between? Well, for the cofunctions, it's always between 0 and pi. For cotan, cosecant, same thing. Both cofunctions. Do the compound inequality, put it between 0 and pi. X is saying what he's always saying, I want to be alone. How do we get x alone there? Multiply through by 3, huh? Multiply by 3, multiply by 3, multiply by 3. It'll cancel. This is 3 pi. 3 times 0 is 0. Between 0 and 3 pi. So what does that mean? That means cosecant will do his first two verticals, this one anyway, between 0 and 3 pi. He'll do his first U-shape up. And the first one's always up, right? Did you notice that? First one's up. Same thing was true back over here for secant. The first one, those first two verticals I'm giving you, is where the up one is. Unless there's a negative in front of the function, that'll flip it. But the normal one, those first two verticals I'm giving you, is where the up U is for secant and cosecant, right? See that? Right here, same thing. Same thing. Between 0 and pi. So for ours, when I get the first two numbers, 0 and 3 pi, I put the U-shape up, and then the next one, you know, going out another 3 pi, be 6 pi, going to have a U-shape down. This will only be at a height of 1/3, because that's the amplitude, and this will be down 1/3. All right, so which of those graphs is doing that? The answer is always A, it seems like, huh? Yeah, it looks like A to me too. Yeah, it's A, it's got to be A, because 0 to 3 pi, can you see it right there? 0 to 3 pi, it's got the upward U there. This one, they moved the U down below the axis. I don't know why they did that, but that's not right. Oh, hey, what's wrong with C? Oh, C's just, it's right, but it's too far up, huh? That's all. The lines, the vertical lines are actually correct, but yeah, they moved everything up. And see, this is up here. It's supposed to be down below the axis. It's not that. It's A. Everybody see that? That okay? Be able to do that in the homework and the multiple choice test. All right, let's move on. All right, so here we are in number 11. 2 secant of x plus pi over 6. So, all right, what do we do first? We grab what's inside the parentheses. We put it between the two bounds for secant. What's it going to be? Secant is a non-co. Yeah, so it's like tangent. Negative pi over 2 to positive pi over 2, huh? Negative pi over 2 to positive pi over 2. You know what to do. X is saying what he's always saying. I want to be alone. So he's a real loner. Subtract pi over 6 from both sides. Like that. Gonzo. And then you got to get a common denominator. So, done this before. Top and bottom by 3. So that'll be what? 3 pi over 6 minus pi over 6, which is 2 pi over 6, which reduces to be pi over 3. On that one, is that okay? All right, 3 pi minus 1 pi is 2 pi over 6, and then reduce it, pi over 3. Other side, same thing basically, top and bottom by 3. So negative 3 pi over 6 minus 1 pi over 6, which is negative 4 pi over 6, which is negative 2/3 of a pi. Am I going too quick there? All those fractions? Like that? So I just took negative 3 pi over 6 minus pi over 6, which is minus 4 pi over 6, and reduced it. So we get negative 2 pi over 3 to pi over 3. That's the first two vertical asymptote lines for the secant graph. So let's go graph the secant. So coming over here, whoops, I need a little more room there. It's going to go between a vertical there, a vertical there. So negative 2 pi over 3, positive pi over 3. There's the first two verticals. And what does the secant graph always do? He's going to do a U-shape up right in the middle of those first two verticals, isn't he? And then the next one's down, and, you know, away you go. And it's going to hit at 2, because there's a 2 in the front, instead of a 1. Okay, so which one? Don't tell me it's A again. Oh, they're not even showing the left side. See, I've got it mostly on the left side. It's just hard to see on these little tiny graphs. I cannot tell at all. They're so small. I don't know. I have to look at them one at a time. I don't know if it's worth our time. So negative 2 pi over 3 to pi over 3. So I'm going to go back and look. It has to have a U shape. Like here's the y-axis right here. It has to have a U shape going up. You know, at the beginning, at the origin, it's going above, isn't it? Like that. And there's a vertical just to the right at pi over 3. And then there's going to be a part going down here, right? So it's got to match that. Let's go back. One more time. We okay with that one? Right? So the U shape was going up at the axis from a height of 2. That was enough to tell. The right answer was B on that one. Okay. So now, let's try these more difficult ones. We'll try number 12. So y equals secant, here, let me write over here. Y equals secant of 2x plus pi over 4 plus 1. Okay, so what are we going to do? Now, the part that's in the parentheses, not the one, the one's outside of the parentheses. You guys tell me, what's that plus, well, I don't know if you know. What's that plus 1 going to do? Yeah, that grabs, yeah, we did talk about that a little bit with some of the other trig functions, huh? That means up 1. That just grabs the whole graph and moves it up 1, doesn't it? So we'll do that at the end. How about? But our first thing is what we always do is we grab whatever's in the parentheses, 2x plus pi over 4, and put it, put it between the bounds. What's the bounds for secant? Negative pi over 2 to positive pi over 2. Secant and tangent are the same. The non-cos. All right. So we got to, this is a little bit harder one. And in the end, we got to move it up 1. Okay. So let's solve for x, like we always do. To that, you begin by subtracting pi over 4. And how do you do that? Got to get a common denominator, like we've been doing. And so multiply top and bottom by 2. So this is 2 pi over 4 minus 1 pi over 4 is just pi over 4. In the middle, that's 2x. Over here, it's multiply top and bottom by 2 there. So it's going to be minus 2 pi over 4 minus pi over 4 is minus 3 pi over 4. Good so far? Everybody okay with all that? All the common denominator stuff? I'm glad to help. Office hours and after class, if you're rusty on, make sure it's a lot of times it's just a little picky stuff that can little mistakes on the exam can get you. Make sure you practice this a lot. So now we got to get x alone. To get x alone, we got to divide by 2. Now remember the easy way to divide by 2 when you have I'll divide by 2 like that. But on the other side, there's I don't want to go over 2 like that. That's kind of hard to deal with. It's true, but it's not the easy way. You just stick the 2 in the denominator, right? Just because that's what it means to divide, is putting it in the denominator. So just put the 2 in the denominator of all 3 of those. So then this is pi over 8, and this is minus 3 pi over 8. Good? So his first 2 verticals are between minus 3 pi over 8 and positive 3 pi over 8. That's where the first. So if I draw the graph of secant, so I'm going to come over here and go, okay, I can do this. So a vertical here, and a vertical here. This is minus 3 pi over 8, positive 1 pi over 8. Right? This one's closer to the y-axis because it's only 1/8 of a pi to the right, positive. This one's 3/8 3 times as far of a pi. Negative, right? That's why I'm drawing it that way. This vertical is further from the y-axis, this is closer. Okay, and then what do I put in there? I'm going to put a U shape. Now, let's be a little careful here. Normally, I just put the U shape right in the center, going up. And this would be at 1. There's nothing in front here but a 1. That's right, that's normal. And then over here, there would be a U shape going down at -1. That's normal, because there's just a 1 in the front here. But this +1 is going to move the entire graph up 1, isn't it? The whole graph's going up 1. So what does that mean? That means this guy will go up to 2, and this guy will go up to 0. Like that. That makes sense? They both moved up 1. The entire graph moved up 1. Like that. So there we go. I'm just going to leave it at that. Whichever of those, I don't got time for looking. I think we'd be better use of our time to do more problems. So just whichever of those graphs does that is the right answer. Is that good? Questions I can answer? Getting the hang of all these graphs? Makes sense? All right. Yeah, so here's a real life I just want to throw in real life applications every now and then. So here's a real life application. You've got this ambulance with a rotating beam, right? Here it is. The ambulance is, the beam is rotating around. It's next to the hospital wall here. The function d equals 14 tan 2 pi t. Let me write that out a little bigger for you. D equals 14 tan 2 pi t describes the distance d in feet of the rotating beam of light from point C after t seconds. What point C? Okay, so here's point C. I don't know if you can see it. This is point C, which is the closest point to the ambulance light on the wall, right? It's the closest point on the wall. It's like if I said, how far from me to that wall? Or me to this wall? Well, I mean like straight line, don't I? I don't mean at a diagonal. The closest between me and the wall is a straight line. Well, that's what C is. C is the closest point to the beam. So that's and so D is the distance from that point to some other point at time t seconds. In other words, as that light rotates, it's going to move along the wall and come back, and move along the wall and come back, right? And so here's a function tracing where that light is, or at least the distance of that light from point C at any time. I could plug in a time, calculate it out, and find out at that instant, at that many seconds, the light is however far on the wall from C, from the closest point. Does that make sense what that function's doing? So I don't know why we would do it with an ambulance light on a wall, but there's times in real life when you got things moving around and you want to track on them, right? This is the kind of function that does that. That's what trig is for. Tracking things that cycle. Tracking anything that cycles like that. So that's a formula for tracking how far the light is on the wall at any instant from the point C, closest to the light. Okay, so what? First off, graph it from 0 to 2. Okay, you guys know how to graph. Tangent, what do? You grab the stuff in the parentheses. If it bugs you, just make that an x. I'll just make it an x because it's tx, whatever. It's just our variable. And what do? You put that between, for tangent, we put it between negative pi over 2 and positive pi over 2. And we solve. Good? That's how we always do it. So how do I solve for x there? Divide by 2 pi. And you know dividing means stick it in the denominator, put it in the denominator. Pi's cancel. This is 1/4. This is x. Pi's cancel. This is minus 1/4. Good? That means the first two verticals for this tangent graph, tangent 2 pi x or 2 pi t, same thing. It's going to be between negative 1/4 and positive 1/4. The 14 in the front, just going to make it go up and down faster, but goes up and down forever. All right, so negative 1, which of these has the verticals between negative 1/4 and positive 1/4? I cannot tell. Oh, and it's got to be tangent, which goes normal snake, like this, huh? So it's not this one. That's upside down snake. So it's not B. Oh, we already know the answer is A because I forced it to tell me. A, yeah, it's A. So this vertical, I guess this vertical is at 1/4. Is that true? How do we know that's at 1/4? Well, this is 2. So half of 2 is 1. So this would be what, 1 here? Is that 1 there? Is that halfway? I can't see the little lines. You'd have to make it bigger. Good so far. So the answer is A because the vertical is at 1/4. This vertical line right here is at 1/4. So we got that. Let's go on to part B, on this one. So now, for what values of t is the function undefined? Well, they're saying, where's their vertical asymptote lines? Because that's what it means to be undefined. You with me on that? Undefined means vertical asymptote. They're basically saying, look at that graph. Okay, so the answer was part A. Look at that graph now and show me where the vertical asymptote lines are. Well, if you look at that graph, I'll go back and look with you in a minute. You'll see that at 1/4, at 3/4, at 1 1/4, and at 1 3/4 are the vertical asymptotes. At least that's between 0 and 2. I mean, there's more. They go on forever. But in the zone 0 to 2, these are the places where there's vertical asymptotes just by looking at the graph. Let's go back and look and see. You've got that copy. I'll come on the YouTube thing with you. All right, so back to the YouTube. So yeah, so this must be 2, 8 boxes, right? So halfway, this must be 1. That's 4 boxes. And so then this must be a half. It's half of 1. This must be a 1/4. So this vertical, so where's the verticals? A 1/4. This one's at 3/4. No, I don't know where the pi came from. I got pi on the brain. 3/4, right? This one must be at 1 1/4 because every one of these marks is a 1/4. You with me? Every one of these marks is a 1/4. So this is 1 3/4 because it's only 1/4 from 2. So boom, boom, boom. So there are vertical, 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 vertical. Undefined. So at those vertical asymptotes, it's undefined. So with that in mind, we go back to here and say, okay, just turn those into decimals. That's the 4 decimal. They want you to just divide them on your calculator, 1 divided by 4. Just turn them into decimals. 0.75, 1.25, 1.75. Now, final question is, what do those mean? I mean, real life. We got a real life ambulance here with the light and the wall. And what does that mean, undefined? And you see the answer is, the beam is shining parallel to the wall at those times. What do we mean, parallel to the wall? Well, in other words, the distance is infinite, right? How far from C? As that light moves along the wall, moves along the wall, moves along the wall, the distance from C to that point where the light is grows and grows and grows and grows. That's when the graph, the snake graph goes up, 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 and eventually the light goes parallel, straight up and down, parallel to the wall. Therefore, it's not going to hit the wall at all, neither end. When it starts going this way a little bit, then the backside will hit again, won't it? But for the split instant when the light is parallel to the wall, then the distance is infinite. It's not even on the wall at all. So that's the vertical asymptote line. That's what that means in the real world. All right, is that good? Maybe not. Let's see. All right, figure shows that you have set yourself up 10 feet. Here you are, 10 feet from the street where your friend will be passing from left to right. If D represents your distance in feet from your friend and X is the radian measure, the angle shown, press D into the trig function X and graph function. Negative angles indicates that your marching buddy is on your left. Oh, okay. That's a tiny little picture. Okay, and they want me to write a function. Okay, I need to make that picture. So this is number 15. It's our last one in this section. So they want, you got a little triangle there. This is X. Can you all see that? This is X. This is D from there to there. X is this angle. So, and they want me to write D equals some kind of trig X thing. I'm going to leave it at that. Some kind of trigonometric, sine, cosine, tangent, secant, cosecant, cotangent, something like that. involving x, they want me to write an equation. So how do we do it? It's all about SOHCAHTOA. Remember what we learned about SOHCAHTOA? X is the angle. So what trig function, what of x, sine, cosine, tangent, will involve d and the tan? Because I don't want to go here. I'll try no. You don't want to go to this side. Why not? Because I don't have anything. I don't know what that side is. I know nothing about that side. So don't go there. Do some trig function, sine, cosine, or tangent of x, that'll involve the d and the tan. Because that's what the two I have something for. So what trig function goes there and there? What is that? Or there and there, huh? Cosine, yeah, adjacent over hypotenuse, huh? Because this would be the side opposite. We don't want to go opposite. We want to go adjacent over hypotenuse, huh? Right, because here's the right angle, the side across. The D is the hypotenuse. So which one is adjacent over hypotenuse? Yeah, that's cosine. Because the cosine of x is what? Adjacent, 10, over hypotenuse, d. Good so far. I'm not done yet. Got to get d alone. Good so far, though? Using the SOHCAHTOA, the cosine of x is the adjacent over the hypotenuse. Now, how do you solve that for d? Multiply by d on both sides. Cancels here. And I get d cos x is 10. Good so far? I just multiply both sides by d, canceled it on the one side, it's on the other side now. How do you finish getting d alone? Everybody good so far? You see what I'm doing? How do you finish getting d alone? We got to divide by the cosine. Boom, d's alone. Now, you can leave it this way, that's true, but that's the same thing as 10 times 1 over cosine, right? Same thing, 10 over cosine, 10 times 1 over cosine, same thing. What is 1 over cosine? Secant. That's what they want you to do. See, that's 10 secant, isn't it? It's 1 over cosine. So there we go. That's the first thing they want. So we just made a trig relationship. We made a real life situation. You're there filming your friend. You're 10 feet from the point they're marching to, but this is how far away your camera is from your buddy, right? And that distance is 10 secant of x, where x is this angle. Your buddy's marching, and the angle is closing, closing, closing. And as it does, the distance away your friend in is 10 times the secant of whatever that angle is from straight to where your friend is, that angle. So there's a relationship between the angle and the distance your friend is away. It's the kind of thing they program cameras with and all the stuff they do. They use this trig stuff.